Hey everyone, welcome to this video on tokenization and byte pair encoding algorithm. So today we are going to explore byte pair encoding. This is used to merge words to create efficient representations for the LLM. And for example, we put a hello text inside a tokenizer. It will give us a token sequence that we can put into a LLM and that can be learned by the LLM. So basically, we are today going to learn how we can create tokens for a text. So we have a text. We are going to create some tokens that would be learned by the LLM. So first of all, we have a challenge in tokenization for the LLMs, and that is of the vocabulary size. So the main problem we face in tokenization is the vocabulary size. If we create different tokens for the entire English vocabulary, that would be too much. And it's just not the English vocabulary. We are going to create it for the Japanese, for different languages. Basically, it is not enough. It is very memory intensive. It will be a massive vocabulary, and we can't do it. So, and even for code, for example, define, return in Python would be a different token than D, E, and F. So that is too much, creating these tokens. This greater library would be too much to create. So we found a sweet spot between, and that is achieved using byte pair encoding. So in the further slides, we are going to understand the byte pair encoding and how tokenization works in LLMs. So first of all, how do we represent tokens in LLMs? And the representation is like any other computer file. We use UTF-8 encoding, which is a way of encoding A to a number, that could be understood by the computer. And Z could be a number 122, and a smiling emoji could be represented by a list of numbers, some list of UTF tokens 240, 159, 152, 138, and they have different byte size. So in a UTF-8 encoding, we have a list of bytes ranging from 0 to 255. So these values could be from 0 to 255, and we have a byte size for them. A is of 1 byte size, Z of 1 byte, and a smiling emoji could be of 4 bytes. But to make it efficient for the LLMs, we use byte pair encoding. So before we understood how UTF-8 works and how we encode simple text into bytes, now we are going to merge these bytes to create special tokens, special vocabulary that could be understood by LLM, and it is much easy. So if we go further, for example, we have an input string of A, B, and C. Maybe A is 97, B is 98, and C is 99. It's of 3 units of 3 bytes. But we found out that A and B occur together a lot of times. So it is the most frequent adjacent pair. So somebody saw that, maybe the algorithm saw that baby in words like baby, or maybe AB, maybe, I don't know, but we just saw that A and B occur together a lot of times. And what we do is we just merge these. So we just merged A and B to a new token of 256. Okay, so initially that we have the range of bytes from 0 to 255 in UTF-8, but for our LLM encoding, we made another token of 256. And what does 256 means? it means 97 and 98. So 256 means 97 and 98, and 97 and 98 means A and B. And why do we merge them? Because they occur together a lot of time. Maybe, that's what the algorithm found out. And we got a new sequence that is much more compressed as 256 and 99. How does byte pair encoding do this? We're gonna find out in the next slide. So what happens is a byte pair encoding algorithm uses a sliding window. Maybe the sliding window is of size 2, and we saw 97 and 98 are occurring together. Okay, for example, how does it work? Let me just show you. So for example, we had a sliding window of size 2. Size 2 means like we got two byte pairs inside it, and we got this window, and we just slide it ahead. Okay, so now the sliding window is on 97 and 98. Okay, so now before it was on 97 and 98, we slided it and it went on 98 and 99. So 97 and 98, maybe they just occurred one time. Then we slided the window, okay, of size 2, and we got 98 and 99 occurring together. Okay, then we slided the window ahead again, and we found out 99 and 97 are also occurring together. We just mark them here, and then we just slide it ahead, and we found 97 and 98 are again occurring together. So maybe 97 and 98 occur together 2 times. Maybe 97 means A, maybe 98 means B, and maybe it means C. We saw A and B, which is 97 and 98, occur 2 times. Now what will the byte pair encoding algorithm do? We'll just merge them. Okay, so what it does, it just merges them. It saw 97 and 98 occurring together 2 times, like here, and it merged it into a new token of 256. Okay, so 97 and 98 means 256 together. Whenever they will occur together, we will just replace them with a new token 256. This made the vocabulary size a little shorter than what it was before, and we just used one memory unit instead of using 2 memory units. So before we were using 2 memory units, and now we are just using 1 memory unit. Same example given here. This is how it works inside the recursion. Okay, so inside recursion, we just saw A and B occurring together, we merged them into 256, and maybe somebody saw, maybe the byte pair encoding algorithm saw that A and B and C are also occurring together a lot of times. So we merged them into a new token 257. So whatever pair will occur together too many times, we will just merge them in. Okay, so same. So A and B now means 256. Whenever A and B will occur together, it will mean 256. Whenever A and B and C will occur together, it will mean 257. And whenever a space and the will occur together, it will mean 100256. Now you're trying maybe be able to understand what I'm saying. I'm saying whenever maybe a word occurs together, it will be given a new token ID, and that would be sent to the LLM. Okay, so the LLM will not read THE, it will read the with the token ID 100256. If we move further ahead, maybe you train the model on like maybe for example you train the model on a medical corpus with a lot of medical data, and it saw the sequence APPE, NDICITS, appendicitis occur together a lot of times. When the word appendicitis occurred together so many times, the byte pair encoding algorithm merged it into a new token a single token. Before it was too many tokens. Maybe it was a token app and IC ETs, but now it just got merged into a new token 4521. Same for a Python code corpus. Maybe that byte pair encoder saw D, E, and F occurring together so many times that it merged it into a new token ID of 882. Similar for return, similar for self. These words occur inside the corpus together so many times that they got merged into a new token ID, that will be easy to understand from your for your LLM. And why we just do that all to decrease the memory slot used. So this is the LLM context window. If we had put HELLO, if we had just put that, it would have used 5 memory slots. But now we just put hello, it just used 1 memory slot. That is just simple. And this is how, so neural network will give a prediction of 256, and we will look inside our token table that what does 256 means. 256 means 97 and 98, and 97 and 98 basically means A and B occurring together. So that's how, we don't put A and B inside the LLM, we put this token 256 inside the LLM. The LLM will predict this token from which we will get these values, from which we will get these predictions, which are just words. Yeah. And that also causes a lot of problems because LLM can't see indispensable. It doesn't see this word, it just sees these tokens. So many times when LLMs hallucinate or create problems, is because of bad tokenization. And tokenization is a very crucial step inside a LLM. Also, the word capital HELLO and the word small h small h ELLO. Okay, so capital H and small h hello are different for your token and for your LLM. That's why we should, understand how these things work, because for a normal human being these are same things, but for LLM it may be different. Yeah, and this is how, your LLMs are processed. So guys, thanks for watching this. I wish you great health and talent. Thanks for your time.